Welcome back, everybody. Today we're going to be doing section 4.2. This section is actually optional, so if you don't want to watch this lecture, you don't have to. But I wanted to include it just because the next section that we have to cover is about the inverse trigonometric functions. And if you haven't spent a lot of time thinking about inverse functions, or if you haven't taken like a pre-calc class before where you talked about inverse functions, it can get a little bit weird. So I wanted to record this extra lecture just in case you wanted a review of inverse functions. So that's what this is. Yeah, so I'll go ahead and get started. I'll try to keep it brief, but here we go. All right, so this is actually section 4.2 if you want to follow in the book. And here's the overview. We're going to do a review of what a function is to begin with. Then we'll talk about one-to-one or injective functions. Then we'll talk about inverse functions, graphs of the inverse functions, and then the cancellation equations. Although, yes, the cancellation equations. So let's just talk about functions first. So what is a function? A function is essentially a box, and it transforms objects into new objects based on some rule that we often call f. So that's the first thing you want to understand about functions, is that it's a very, very abstract, generalized concept. What we want to do is we want to be able to talk about these rules or these procedures, these functions that can transform things into other things, and we want to explore that behavior. So the only requirement to make this process a function is that only a single object can come out of the box at a single time. And that object that falls out of the box is called f of x. So the general idea is you take something, you put it into the box processes that something, and then out pops f of x. That's the output. Um, so not every relation is a function. You can have data sets where a single input will give you many, many outputs. For example, you could put in the number 3 and you might get the output 7, 8, 9, 10. So if you put in the number 3, but you get out 7, 8, 9, 10, then you're not working with a function. You're just working with a relation. So functions specifically can only get one output at a time. So if you put in the number 3, you better only get out one number. If you put in the number 2, you better only get out one number. You don't want to get two things out at the same time. So classically and graphically, you can test for this behavior just by using what's called the vertical line test. So if you remember that, that's basically what it is. The vertical line test is you testing to see if the relation you're working with is actually a function. So if you draw a vertical line and your vertical line only touches the graph of your relation once, then it's a function. But that has to be true for every possible vertical line. So you have to pass vertical lines through every point, every input point of your function, and then you see if it touches the graph at more than one point. If it touches at more than one point, then it's not a function. All right. Another thing is the notation. So the notation for functions is actually very helpful and very good. And in my experience, students that struggle with the concepts of functions largely are having trouble with the notation itself. So let's review it really quick here. For one, the symbol that goes inside these parentheses, that's the input. That symbol is arbitrary. It does not have to be an X. It doesn't have to be a letter. It can be any symbol that you want just to act as a placeholder for the input. So the input is just whatever you want to be able to put into this box. We're going to use the letter X just because it's a common usage, it's a convention, so we use X. Now, this little piece over here, this letter F is what's called the rule or the name. So that's like the label on the box, the name of the box. It's like you put a sticker on the side of the box, and that sticker essentially says what the box does. So that's what the letter F means. Now, perhaps the most important part is this. The entire symbol as a whole represents the output, the output. And if you can wrap your head around that, it'll make working with these symbols and working with these functions a lot more intuitive. That whole symbol f of x, that's the output of the function when you put in the number x, right? So don't think of f of x as the box itself. Think of f of x as the object that falls out of the box after x passed through the box, or went into the box, I should say. So that's what the notation means. Here's a good example. Let's look at the function f of x equals 3x plus 1, right? So here, x is the input, and f is the rule that's given by the sentence, multiply by 3 and then add 1. So the label on the side of the box, the label F, basically says that sentence. And the sentence is, hey, if you put something in this box, it's going to get multiplied by 3 and have 1 added to that result. So that's the sticker on the side of the box, F. Now, what is the output? The output is what you get after you multiply the input by 3 and add 1. So that's f of x. F of x is 3x plus 1, the output of the function. All right? There you go. And here's a diagram. Okay, so just a quick review of functions. Now, what we want to do is we want to talk about inverse functions, and we can motivate this with a question. The question is, if we have a function f, does working backward from the output to the input always constitute a function itself? So ponder that for just a minute. Just think about if we started with the output and worked backward to the input, does that process constitute a function? All right, so if you're skeptical, which you should be, the answer is not always. The answer is sometimes, just sometimes. And we're going to explore now exactly when that is possible. So in particular, we say that a function is invertible if and only if it's one-to-one or injective. That's another way of, that's another phrase for, or sorry, that's another what word am I thinking of? That's just another word for one-to-one, injective. So if your function is one-to-one, then it's invertible. All right, so here is the definition. We say that a function is one-to-one or injective if it never takes on the same value twice. So this is different than just the definition of a function. So make sure to read this and think about this carefully. What we're saying is that for any distinct x1 and x2, I should say distinct here, should add that in. They cannot be equal. For any distinct x1 and x2, the outputs will not be equal. So in other words, this means if you have two different inputs, like x1, or sorry, we'll say x1 and x2, if I put those into the box, do I get the same value as an output? If I get the same value as if I get the same value for the output, then our function is not one-to-one. It's not one-to-one. So specifically what we're looking for is we're looking for functions where the same height, I'm sorry, the height is never achieved twice. That's kind of the idea. What's nice is that in two dimensions, in the plane, this definition is equivalent to a very easy to visualize theorem, which is this, the horizontal line test. So the horizontal line test says that a function is one-to-one if and only if every horizontal line crosses the graph of the function only once. And we're going to see some examples in just a moment here. But stated equivalently, this means that if any horizontal line intersects the graph of graph of a function more than once, then the graph does not represent a one-to-one function. And so that function does not have an inverse. So let's look at an example here. Let's say, okay, I'll just draw my xy coordinates or xy axes here. Let's look at a function that looks like this. So here's a function, oops, let me do this. So here's a function that is one-to-one. And the reason is that if you pick any two distinct inputs, you'll never get the same output. But we can use the horizontal line test to see it immediately. So let me pick a different color here. So I'm just going to pass horizontal lines through my function, right? Notice how those horizontal lines only intersect the function at a single point, right? And so there's no place where I could draw a horizontal line and hit the graph twice. So that means that our function is invertible. So we could invert this function. It's one-to-one, it's invertible. Now, here is a counterexample. Here's a function that is not one-to-one. Actually, I'll use the one that we're going to explore in detail in the next section. Here we go. There we go. That graph looks familiar, right? So check this out. If I try to draw a horizontal line almost anywhere, I'll draw one just here. Notice that it hits the graph many times. It hits the graph here, and here, and here, and here, and here, and here. So what this means is that this function is not invertible as it stands. So basically, we can't reverse the process of this function and start with an output and get to the input that corresponds to that output because the function's not one-to-one. Now, got to be a little bit careful here because that doesn't mean that we can't tweak things the right way to get something that is invertible. And that's what we're going to do in the next section. But let me use a simpler example for a minute. Let's look at x squared. I'm going to move this over here. Let's look at x squared, everyone's favorite parabola, right? So x squared looks like this, looks like this. Now, the graph y equals x squared and the function x squared, it's not invertible. It's not invertible as it is. And you can see it with the horizontal line test. Boom, boom. It hits that graph twice. So because of that, it's not invertible. However, what you can do in some cases is you can restrict the domain. So basically cut cut some of the graph away, and then you might have something that is invertible. So in this case, one thing that we could do is this. Let me erase this for a minute. I'm just going to erase the left-hand side. So in other words, what I'm doing is instead of looking at the function x squared over the entire real line, I'm just going to look at it over the positive x-axis or the non-negative x-axis. Well, now the graph does pass the horizontal line test. So this is actually invertible. There you go. So this is kind of a lead into what we're going to talk about when we look at the inverse trigonometric functions, because for those, we have to make a domain restriction to be able to invert them. And that turns out to be a critical choice that we'll talk about later. But the horizontal line test is an easy way to check to see if your function is invertible. All right, so now what is an inverse function? So let's start with a function that's actually invertible. So let f be a one-to-one function with domain A and range B. Then its inverse function is denoted with this symbol, and it's pronounced f inverse. And that inverse function has domain B and range A. So the domain and the range are switched for an inverse function. And how do we define the inverse function? It's defined like so. F inverse of y is equal to x if and only if f of x is equal to y for any y in B. So this is essentially how you define the inverse function. You define the inverse function in terms of the original function, but you're essentially saying that the the input, here you go. If you want to be able to get to this input by putting in this output, then you need this relationship, that f of x equals y. Now, intuitively, what's kind of fun about this is that inverse functions undo the process of the original function itself. So for example, if the original function says to, like we saw before, multiply by 3 and then add 1, the inverse of that function would basically unwrap things. It would say, okay, I want you to subtract 1 and then divide by 3. Does that make sense? Yeah, so think about that example for just a minute. Ponder it for just a minute. All right. So yeah, in particular, the order of that process is reversed. And yeah, the order and the elementary options are inverted. So let's look at this example here. I'm wondering, hold on, let me look ahead for just a minute. Okay. All right, so let's look at this example, x cubed plus 2. So first of all, is this function even invertible is the first question you should ask. And if you can remember what the graph looks like, you'll see that it is. So let's do a quick sketch of the graph. Here we go. It looks something like this, where this is the point 2. All right, so this is what the graph looks like, x cubed plus 2. Notice that it passes the horizontal line test, right? No matter where I draw a horizontal line, it's only going to touch the graph once. So this is actually invertible. Now, how do we compute the inverse function itself? Well, it's not so bad. Pretty much all you do is you solve this equation. Oops. You solve this equation for the input, x. So this is where I want to re-emphasize something. Remember that f of x, that symbol that I just highlighted, that's the output. That's the output of the function f. So f of x as a symbol is like it's like its own object. So you don't want to do anything to that object. You don't want to try to like peel the pieces of the symbol apart. Just think of f of x as a single object, and that's the output of this function f. So if we want to invert this function, what we're going to do is we're going to solve this equation for x. So we need to get this by itself. And the way we're going to do it is just with elementary algebra. So here we go. Um, here we go. So here's what you do first. Subtract 2 from both sides, then take the cube root of both sides, and then you're left with this result right here. All right. So if you look at this equation at the bottom, what it's telling you is it's telling you the input that you would get if you were given an output f of x. So if you take an output f of x and you subtract 2 from it, and then you take the cube root, that'll give you x. And that is the inverse function. So now all we need to do is just relabel it. So we can relabel everything. We can relabel this as f inverse of x, and we can relabel this as x because those symbols are arbitrary. And that's the inverse. That's the inverse. Now, one thing I want to do real quick before we go to the next slide. Notice the order here, right? So look at what f does. What does f say to do to its input? It says cube the input, then add 2. What does f inverse say to do? F inverse says subtract 2 from the input, and then take the cube root. So it's quite literally reversed, like, right? It reverses everything. So that's what an inverse function does. Okay, so um, what's really nice about inverse functions is the graphical interpretation. And one of my favorite examples, which I don't include here, is logarithms and exponentials. So a lot of times in my classes, before we start exponentials and logarithms, I'll be like, oh, who knows how to draw the graph of an exponential? And there's usually a handful of students that do. And then I'm like, okay, who knows how to draw the graph of a logarithm or a logarithmic function? And almost nobody says, I know how to do it. But logarithms and exponentials are inverses of one another. So if you know how to draw an exponential, you know how to draw a logarithm. Now, how do you do it? Well, remember that the domain and the range of an inverse function are switched. So if you switch the domain and the range, what you're doing is you're switching the inputs and the outputs. So graphically, what that means is that the x values and the y values on the graph are switched. Yes, so they're switched, which makes sense, right? Y's are the outputs normally, X's are the inputs normally. So if you want to look at the inverse, those values switch. The only values that are not going to change are the ones where the input and the output are equal. So if your input is equal to your output, then those results are identical, they're the same. So they're not going to switch per se because they're like the same thing. So in other words, when is that true? Well, that's when this is true. So the points that aren't going to move are the ones where the input is equal to the output, right? Output, input. So this is the line y equals x. And so what this tells us is that the graph of a function's inverse is reflected about the line y equals x. So here, look at this example down here. I've got the graph of x squared again, but I restricted the domain. I restricted the domain so that it was only the non-negative x-axis. And so that's x squared. And if I want to look at what its inverse function looks like graphically, I just reflect x squared over the line y equals x, the diagonal, and then I get this result. And so that's the graph of square root of x. And square root of x is the inverse function of x squared. There we go. So, like I say, if you can graph a function, then you can graph its inverse, if that inverse actually exists. Um, yeah, one note here. This holds for any invertible function. Oh yeah, I just said this actually. This holds for any invertible function. So if you know your function passes the horizontal line test, you can graph its inverse just by reflecting f of x over the line y equals x. And there you go. Easy peasy. Okay, so next, let's talk about the cancellation equations. So this is, I would say, people's most favorite part about inverse functions. because it's so handy when it happens to work. But the cancellation equations essentially say this. If you've got a function f and you've got an inverse function, well, that function is the inverse if and only if f inverse of f of x equals x, when x is in the domain of f. And vice versa, f of f inverse of x is equal to x, when x is in the domain of f inverse. So that's a mouthful. That's a mouthful. There's a lot of f's and a lot of f inverses flying around. So let's make some more sense of it. Remember what I said a moment ago where I was talking about how an inverse function essentially undoes what the original function does? So what this is saying is that your function, you'll have the correct inverse function if you can first apply f to an input and then apply the inverse to that result, and you end up where you started, right? So it's like if you perform the operation and then you undo the operation, you should end up where you started, no change, x, right? You should end up with the input that you started with, right? And that's what indicates that you do have the correct inverse function because inverse functions undo what the original function does. Now, one of the catches here is that it has to work both ways. So you can't guarantee that it's going to be the inverse unless you can do these these undoing processes in both directions. So you would also need to be able to start with the inverse and then apply the original function. And if you end up with where you started, then everything's all good. There you go. So why do we call them the cancellation equations? Well, because if you want to think of it symbolically, it almost looks like these things are just canceling each other out, right? It almost looks like you could just go, oh, F inverse and F cancel each other, and then you're left with X. Oh, F and F inverse cancel each other, and you're left with X. So that's why we call them the cancellation equations, because as long as the domains and the ranges are correctly aligned, then these processes cancel each other out. Um, one example that I like to use, if you have siblings or if you have little siblings, think about this, for example. Let's say you clean your room, right? You go and you clean your room. You started with a dirty room. You spend the afternoon cleaning it. Now you have a tidy room. Then your sibling comes along and re-dirties the room. They undo what you just did. Now you end up with a dirty room again. So your cleaning process was the function, and your sibling's uncleaning process, dirtying process was the inverse. So what do you end up with after you do those in order? You end up with where you started, a dirty room. There you go. So that's what the cancellation equations are. All right, so let's go back to that example we did earlier and let's just verify that we did calculate the correct inverse for x cubed plus 2. What we're going to do is we're going to compose these two functions in both orders. And if we do that, we should end up with x both times. So here we go. Yeah, so first we'll note that the domain for both of these functions is the entire real line, so we don't have to worry about issues of domains and ranges lining up. Um, yeah. In fact, the ranges are also all real numbers, so there's no issue at all. So let's do the first composition. Let's do the first composition. Plug f of x into f inverse. So we're going to plug f of x into f inverse, and then this is what we get. And then you'll notice that everything cancels, right? The 2's cancel, and then you're left with cube root of x cubed. The cube and the cube root cancel, and you're left with x, which is the input you started with. Now do it in the other order. Apply f inverse first. So plug f inverse into the function f, like we're doing right here, and then again, you'll see everything cancels out. Everything cancels out. The cube root and the cube cancel out. Then you're left with x minus 2 plus 2, which leaves you with x. So indeed, the inverse that we calculated is the inverse function of f, because the cancellation equations are valid here. All right. And that's it. So yeah, I just wanted to do a quick review of inverse functions. If you've seen that before, or if you remember that, great. If you didn't, I hope this helped a little bit. There's no homework assignment associated with this lecture because it's just optional. But you can always do some practice problems if you'd like, if you go to section 4.2. But on that note, I'm going to call it a day, and I will see you all soon for section, ooh, what is it? Section 6 point, ooh, I lost it. Where is it? What is it? Section 6.2. Yeah, 6.2, where we talk about the inverse trigonometric functions themselves. All right. Have a good day, everyone. I'll see you next time.